Hello dear student, welcome to the third lecture in tensor analysis. In the previous video, we have learned about notations and conventions. In this video, we will learn about different types of vectors. Vectors are mainly classified as covariant, contravariant, mixed and invariant tensor. So in this video, we will look into the concept of contravariant vector, covariant vector. Then we will extend our discussion into contravariant, covariant and mixed tensor. And then we will look into the Kronecker delta tensor. As we have already seen, the tensors can be described only in a coordinate system, only in a specific space. And we have learned that tensors remain invariant under coordinate transformation. That is, tensor as a physical quantity remains invariant, but its components changes with the changes in the coordinate system. Consider a coordinate system, say x and y. So any vector in this coordinate system, say A, can be described as a linear combination of the basis vectors, say x cap and y cap. So let me write vector A in tensor notation. Vector A is also denoted by an underbar. Vector A can be written as a linear combination of x cap and y cap. In this vector, we can see it can be written as 4x cap plus 5y cap if I call this as my y-axis and this as my x-axis. Now, let me change the basis. That is, let me change the basis x dash and y dash such that x dash is equal to 2 times x cap and y dash cap is equal to y cap itself. Now I have changed my basis. If I change my basis, then this is my new x dash cap and the y cap and y dash cap remains the same. Now the same vector A can be represented as 2x cap dash plus 5y cap dash. Now you can see that when I have doubled my basis, my component has become half. That is, when I have multiplied 2 with my basis vector, my component has become half, that is from 4 to 2. So if the components of a vector varies inversely with the change in the basis, it varies contrary to the change in the basis, such vectors are known as contravariant vectors because they vary in contrary to the change in the basis. They are known as contravariant vector. So vectors whose scale changes inversely to the changes in the scale of the reference axis, they are known as contravariant vector. They are denoted by a subscript. Examples of contravariant vectors are velocity and displacement. Here, velocity is a contravariant vector. So this basis is denoted by a subscript, and contravariant vectors are denoted by a superscript. It is denoted by superscripts. So the components vary contravariantly with the basis. So basis is denoted by the subscript, whereas the components are denoted by the superscript. Examples of contravariant vectors are velocity, displacement, force, or anything that we use commonly are contravariant vectors. Now, if there are vectors such that its components vary as same as the variation in its reference frame, then they are known as covariant vector. The components of the covectors change in the same way as the changes in the scale of the reference axis, and they are known as covariant vectors. If a component of a vector changes covariantly, it is known as covariant vector. If the components of the vector changes contravariantly, it is known as contravariant vector, and this covariance is denoted by a subscript. As you can see, the force and the momentum changes covariantly, and the examples are the gradient and also all the vectors you are going to see in the Riemann space or the Minkowski space. That is, when you go to relativity, you will come across covariant vectors, but in normal spaces we are dealing with contravariant vectors. So just realize that it is not the vector which changes, but the component is the one which changes. The tensors and the vectors are invariant under coordinate transformation, so they remain invariant, they remain unchanged, but their components vary with the variation in the reference axis. So covariance and contravariance describe how the quantitative description of a general geometric or physical entity changes with change in the basis. If it changes with the basis, it is covariance. If it changes contrary to the basis, it is contravariant. Now, based on how an entity changes with the change in the reference frame, the tensors can be mainly classified as covariant, contravariant, invariant, and mixed. So far we have seen only about the vectors, that is first order tensors. The first order tensor can either be covariant or be contravariant or can be invariant. Invariant means it does not change with the change in the basis. For example, a scalar quantity, say mass remain invariant under any coordinate transformation. Therefore, it is an invariant vector. Whereas tensors can be both contravariant and covariant at the same time, and such tensors are known as mixed tensors. Now let us look into how the transformation or how the components of a contravariant vector change. So to examine the properties of transformation of a contravariant vector, let us choose the displacement vector dr. We know that displacement is a contravariant vector. Now let us see how the components of the displacement vector, here the dx1, dx2 and dx3 are the components of the displacement vector. Now let us see how these components vary when I change the reference axis x1, x2 and x3. Suppose I change the reference axis x1, x2, x3 to x1 dash, x2 dash, x3 dash. Now I want to know how the quantity dx1 changes. So using partial differential equation, let's say dx1 dash is the component of x1 dash cap in the new coordinate system. Then dx1 dash can be written using partial differential equation as dou x1 dash divided by dou xj into dxj, summation over dou x1 dash divided by dou xj into dxj. This quantity just says how much of x1 dash is there in the xj component into the xj component. So this comes from the partial differential equation. Now using Einstein's summation convention, we can just get rid of this summation symbol, because when we have two indices repeated, the summation is implied. So using Einstein's summation convention, we can write dxi dash is equal to dou xi dash divided by dou xj into dxj. Now I represent dx1 dash as ai, and any quantity A superscript j can transform according to the equation. This comes directly from this equation. dxi dash is represented as ai dash, where dxj is represented by a superscript j, because we know that this is a contravariant vector. This is a component of a contravariant vector. We are talking about displacement. So aj is a component of a contravariant vector. So any component of a contravariant vector changes in the transform in the coordinate transformation as axi dash, that is the new component in the new system will be equal to dou xi dash divided by dou xj into aj. Here summation is implied and the summation comes ranges over the dimension of that space. Now you can see that this quantity here dou xi dash by dou xj actually says how much xi dash is along the xj component, or it is just the direction cosine or the cosine of the angle between the xi and the xj system. That is the cosine of those maybe x1 dash and x2, or maybe x1 dash and x1, or maybe x1 dash and x3 and so on. This just says us the direction cosine of that quantity, direction between those two axes. Now let us also define dou xi dash divided by dou xj by another component aij. Now I can write ai dash is equal to aij into a superscript j. Therefore, any set of quantity aj that can transform according to the equation ai dash is equal to dou xi dash divided by dou xj into aj is defined as a contravariant vector. And the indices of a contravariant vector are written as superscript. You can see that since it varies contrarily, the variation component, it comes to the denominator. Xj comes to the denominator. You will see the other way in the next. So, in the same manner, let us define how the transformation occurs to a covariant vector. We have already said that gradient is a covariant. Gradient transforms covariantly. So let us take the gradient of a scalar field phi. Now I also transform this into from the x1 xi to the xi dash frame. Using the transformation, I want to know how the component dou phi by dou xi changed to the new. So dou phi dash by dou xi dash, this is the new component. It has derived from my existing component, that is dou phi dash. So I can just using the partial differential equation as I have done, I can just write the terms as dou phi dash by dou xj into dou xj divided by dou xj dash. This is written using the partial differential equation. Using Einstein summation convention, I can get rid of the sigma sign and write dou phi dash divided by dou xj into dou xj divided by dou xi dash. Now we know that the phi is a scalar field. Therefore, the scalar remain totally invariant under coordinate transformation. Therefore, this component of a scalar in the x space as well as in the x dash coordinate will be the same. Therefore, phi dash can be replaced with phi. And we have just seen that the transformation vectors, that is the displacement vectors, say x, y, z, all vary contrarily. They vary as a contravariant vector. That is, its components vary inversely with the change in the basis. We seen that displacement is a contravariant vector. Since all these x, y and z are normal vectors, a position vector or displacement vector, the actual representation is x superscript I, because it is a contravariant vector. Therefore, instead of x subscript I will be using x superscript I from now onwards. So, this quantity, the quantity here can be represented as dou phi dash. The quantity dou phi dash by dou xi dash now becomes dou xj. That is, now the dou xj from here changes to dou superscript j divided by dou xi dash. I also goes to the superscript because it is a contravariant vector, and dou phi divided by dou x superscript j. Now I like to represent the dou phi dash by dou xi dash as ai, and any set of quantities can transform according to ai dash is equal to dou xj divided by dou x dash I aj. You can see that the j components are both in the numerator. So, if any quantity, any set of quantity aj, j here is in the subscript because it is a covariant vector. So, any set of quantity aj which can transform according to the equation ai dash is equal to dou xj into dou xi dash. aj is defined as a covariant vector, and these indices can be written in the vector form as subscript. Now, there are certain exemptions in the Cartesian coordinate. So far we have learned how it look in the general coordinate system. In the Cartesian coordinate or in the orthogonal coordinate system, we have certain exemptions here. So the contravariant vector, we have defined contravariant vector aj as a vector which can transform according to this equation. That is, j comes to the denominator. Now we have already seen that since j and I, xi and xj itself is contravariant vectors, these integers can go to the superscript. This is a more apt representation. Therefore, I can write this equation similarly as ai dash is equal to dou x, I goes to the superscript and j goes to the superscript aj. Now, let us define the covariant vector. So, covariant vector aj is a vector, is a component of a vector. See, vector is not the one which is transforming, only the component of the vector which is transforming. So, component of a vector that can vary, change according to the equation dou xj dash divided by dou x dash I is equal to ai dash. Now, in the system is Cartesian. If the coordinate system is Cartesian, all the xi, x represent x, y and z components, and also if you are talking about some xi dash, it will be some combination of this x, y and z axes. We know that the h parameter of the coordinate of Cartesian coordinate is 1, 1, 1, whereas the h parameter of a cylindrical coordinate system has another component here, and that of a spherical coordinate system also has components. So, Since the h parameter or the scaling factor is 1 is similar for all the coordinate, it doesn't matter if I reverse this equation. That is, dou xj by dou xi dash can be reversed as dou xi dash divided by dou xj, and the system and the equation remains invariant. Therefore, this equation becomes similar to the contravariant vector. See, if I reverse this equation, both these equations will become similar. So, in a Cartesian coordinate, both the covariant and the contravariant vectors are similar. Therefore, there is no difference between the contravariant and covariant transformation in a Cartesian space, whereas this distinction is evident in when we are working with the Minkowski space or the curved Riemannian space of general relativity. This variation is real and it can be observable. Now, let us extend our discussion from the rank 1 tensor, that is vector, to rank 2 tensors. So, in rank 2 tensors, we have said that they can either every indices can vary contravariantly, or every index can vary covariantly, or one can vary covariantly and another can be a contravariance. So based on that, there are contravariant, covariant and mixed tensors. See, the contravariant tensor I and j varies contravariantly if A, K, L is a component of a tensor. That is, tensor is represented by a matrix. So, AKL must be any component, any matrix element. Here, in the case of vectors, we know that vectors can be represented as matrix also. A covariant vector can be represented, a contravariant vector, that is the vector we usually use, are represented by these equations, that is using a row matrix, using a column matrix A1, A2, A3, whereas a covariant vector can be represented using a row matrix, say A1, A2, A3. Here I have given subscripts and superscript accordingly. So, a vector representation just consolidate to either a column matrix or a row matrix. But in the case of a matrix, in the case of a tensor, the variation depends on, its representation is as a two-dimensional vector, two-dimensional matrix. So, any element AKL can be a component of the vector, an element of a matrix KL. Therefore, any element KL can transform according to the equation. Since both are contravariantly varying, K transforms to I, the component, as dou xi dash divided by dou k, remember, and the ith component varies as dou xj dash divided by dou l. Now, if it is a covariant tensor, that is, if both the components vary covariantly, then the k varies as, the kth index varies as dou xk divided by dou xi dash, it is covariant, and L changes as dou xl divided by dou x dash j. If it is a mixed tensor, then one index may vary covariantly and another can be a contravariance. Therefore, K can transform, since K is a contravariant transformation, K can transform as dou xi dash divided by dou xk, whereas L can transform as dou xl divided by dou x dash j. See this partial derivatives. The number of partial derivatives actually depends on the rank of a tensor. When we were looking at the rank 1 tensor, that is vector, there was only one cosine, the direction cosine here. But as the rank of the tensor increases, here the tensor is a second rank tensor, so we have two partial derivatives or the direction cosine. And if we were dealing with a 3 rank tensor, then the direction cosine would be 3. So for a scalar there would be no direction cosine, that is the components remains the same. Whereas for a vector we have one direction cosine, and the direction cosine itself is denoted by a matrix. That is, when we are transforming a vector, it is denoted, the transformation is done by another matrix. Hope you know these transformations. We have done these transformations during Cartesian to orthogonal coordinate system, Cartesian to spherical or Cartesian to cylindrical. So we have done this transformation. This is a matrix Aij, and the transformation can take place accordingly. Now if we are dealing with a mixed tensor, we also have two different partial derivatives or the direction cosines. Now let us see Kronecker delta. We have discussed about the properties of Kronecker delta in our previous video. So based on what we have discussed today, the Kronecker delta actually appears to be a mixed tensor. Hope you remember in the last class I have asked you to write Kronecker delta Ij also as Kronecker delta Ij. Hope you remember. If I write Kronecker delta Ij as this in this form, then it turns out to be a covariant vector. But this representation of Kronecker delta, where one index comes to the subscript and another goes to the superscript, is the apt representation, because Kronecker delta turns out to be a mixed tensor. So let us see whether Kronecker delta is actually a mixed tensor. We know that the transformation equation of a mixed tensor actually transforms according to this given equation, when L changes covariantly and K changes contravariantly with respect to some axis I and J. Now if Kronecker delta is a mixed tensor, then it should also vary according to the same equation. So I replace C with delta and it has to replace according to this equation. So now let us evaluate the right hand side and see if we get the left hand side. So when I evaluate the right hand side, I have the equation here, and using the properties of Kronecker delta, we know that this term will become 1 only when K is equal to L, and for all other formation, for all other K not equal to L, it will become 0. So this equation reduces to dou xi dash and K is replaced by L, dou xl and dou xl divided by dou xi dash. These two can be cancelled out and I can write it as dou xi dash divided by dou xj dash. Now xi dash and xj dash are both independent coordinates, that is both are orthogonal coordinates. So there is no chance that any component of xj will lie along the xi axis. That is, this quantity will exist only if I is equal to j and vanish for every other quantities. As we already know, this actually represents, this quantity here represents the direction cosine. So the direction cosine is 1 only if the cosine is taken with respect to its own axis, and it goes to 0 for any other combinations. So this can be written as delta ij dash, because this happens only when I and j are equal. So I can just substitute this to my existing right hand side and see I can get dou xi dash divided by dou xk into dou xl divided by dou x dash j into delta lk dash actually gives me delta ji dash, and hence it is proved that Kronecker delta is a mixed tensor. So Kronecker delta, the component of the Kronecker delta actually varies as a mixed second rank tensor, and the Kronecker delta components are same in all the rotated systems, so it is also known as isotropic tensor. We will see different types of isotropic tensors when we look into the spin systems. The spin of electrons and all, we will see different types of isotropic tensor. Hope you have seen some in the when you have learned about the group theory. In group theory chapter also we will come across some of the isotropic representations. So isotropics are mainly something which remains invariant under rotations. So you have seen many groups related to that also. In quantum mechanics, this will come into play when we are discussing about the spins of the systems. So let us now look into some of the problems here. So the first problem is, if AI and BJ are components of a contravariant and covariant tensor of rank 1, that is, they are vectors, covariant vector as well as a contravariant vector, show that Cij is equal to AIBJ. Remember, Cij, it have two components, so it have to be in the form of a matrix. I don't say it have to be a tensor because it have to obey certain rules which is definitely occurring for tensors only. So it have to be in the form of a matrix, whereas AI and BG are in the form of a row metric and a column metric. Okay. So I have here AI. As you can see, AI, my AI here is a contravariant vector. So AI can transform according to the equation dou xi with respect to some other coordinates, say k dash, is equal to a k dash. Now I have bj. Bj is a covariant vector, so Bj will transform according to the equation dou xj divided by, with respect to some other coordinate system, say L, is equal to Bj dashed. So let me multiply this equation Bj dash into ak dash, then I have dou xk dash divided by dou xi into dou xj divided by dou xl into ai bj. Now this is written according to the Einstein summation convention. If I am not using Einstein summation convention, there can be an ij here. This varies according to the ij. So see here, we have seen this. We have seen this in our previous slide, as this is the transformation equation for a mixed tensor. So if this is a transformation equation of a mixed tensor, a component of a mixed tensor, then the term here have to be a mixed tensor. So this have to be a mixed tensor of Cj. Hope you are clear with this. You can also see this in a matrix form way, because rho I actually is a contravariant tensor, so it can be represented as a row matrix, where Bj is a covariant tensor, it is represented as a column matrix. So you know that when you multiply a row with a column, what you will get is a 2 by it's a component vector, a two-dimensional vector. So here what you will get is a mixed tensor with the component j and I. Hope you are clear with this. Now let's move on. Write the equation of transformation of A I J K. Okay, let's write that. A I J K. Okay, I varies contravariantly, J varies contravariantly, whereas K varies covariantly. So if I varies contravariantly, what I can write is dou xi. It varies contravariantly according to some other, say P dash. Again, J varies contravariantly, so it can also xij varies contravariantly with respect to PQ, and K varies covariantly, so K varies covariantly dou xk divided by dou x dash say r. We have sigma. If you are not using the Einstein summation convention, then sigma ijk will be equal to a dashed of p q r. This is the transformation equation of the vector a j k. You can also write in the reverse way. That is, aijk is equal to reciprocal of this transformation equation into a dash of pqr, it according to your taste. Now let us evaluate delta function. We know that delta function is the mixed tensor. So here we have the delta function delta ji. We know that delta ji is a mixed tensor. So the transformation equation can be condensed. We have written the transformation equation, but it can be condensed as dou xi by dou xj, and also delta ki actually gives us the direction cosine. So it is dou xi divided by dou xj. We can write it directly, or you can go to the transformation equation. You can go to the transformation equation of a mixed tensor. Then you will get a delta here. Then according to the property of the delta, this equation will come to this concentrated form. So you can write it either directly or in stepwise. So what we have here is delta ji into delta ki. So what is dou xi divided by dou xj into dou xi divided by dou xk. So this whole equation will exist only if j is equal to k. right? If it exists only if j equal to I and k equal to I. This implies that this whole equation exists only if j equal to k. We can't switch the integers between the subscript and the superscript. Therefore, this equation turns out to be some other delta. Delta I remains the same. This can be written as delta ij or can be written as delta ik. Both expressions are the same. So, this will become delta ji or will become delta ki. Now let's do another exercise. Show that if the components of any tensor of any rank vanishes in a particular coordinate system, then they vanish in all coordinate systems. So let us try with the very easy one, the rank 1 tensor. So the rank 1 tensor, say we can stick on to a covariantly varying tensor. If it varies covariantly, then I have aj transforming according to aj divided by xi dash to j. So this is how my vector vary when I transform from the xi system to x dashed I system. Okay. Now the equation says me that the component of every component vanishes in a particular system. That is, say my all xi's turns out to be 0. Then it vanishes at every coordinate system. See, if all my xi's or all my xj's turns out to be 0, then all my these terms will turns out to be 0. If all my these terms turns out to be 0, it depends that this term, that is ai dash, will become 0. We know that ai dash represent components of the same tensor in the x dash coordinate. Therefore, if in the x coordinate all the xi's or all the components turns out to be 0, then it is indeed 0 in the other coordinate systems also. We can also do this with a second order tensor. In second order tensor, we have two direction cosines, one of which will turns out to be 0 for every xi, and indeed the component ai dash itself turns out to be 0. So this property is very important when we are dealing with general relativity. That is, when we are dealing with the Riemannian space, the Riemannian manifold. If the quantity is expressed as tensor in any of the coordinate system, it have to be a tensor in any other coordinate system, not because of the geometry but because of this property. That is, any quantity, the quantity actually remains the same, but only the space in which it is defined varies, and the space definition actually is given from our side. So the quantity remains the same irrespective of the space we are looking into. Now for your practice, please try the following equations. That is, write the transformation of this given tensor. This is a mixed tensor. Evaluate these delta functions. Now show the velocity of a fluid at any point is a covariant tensor of rank 1. This you can find information of velocity of a fluid at any point. Go for an internet search and see and find that its velocity is a covariant tensor. Give you a hint, its velocity actually varies such as a gradient varies. So it is a tensor of rank 1. Please find the equation for this and find it is a covariant tensor. Also, please try exercise 2.6 from your reference text of Efkin and Weber, 6th edition, page number 138. And also from another textbook, this is not your reference, but from the 7th edition of the same exercise, 2 questions, 4.3.1 and 4.3.3 for your reference. Now, for fun, please identify these given equations and find the covariant, the contravariant and the mixed forms which is given here, and please try to account for the same. These are my references. Thank you.